So in addition to wind, streams and rivers play an important role in soil redistribution across landscapes. And the authors talk about 3 different zones that you have with streams and rivers and moving materials. The first is the erosional zone. It's places where material is picked up and lost from a system. Then you have transfer zones. And lastly, depositional zones. This is figure 3.7, which is a graph that shows differences between discharge and the gradient, so how steep the gradient is. And essentially, as you go to higher and higher discharge rates and higher vertical gradients, you're more likely to have an erosional zone, but as discharge declines or the gradient declines, you're more likely to have deposition. All the details here about whether you have braided gravel beds or meandering sand beds, for example, can be effectively ignored and just really focus in on the role of discharge and the gradient in determining whether they have erosion, transfer, or deposition. This might be a slightly easier way to think about it. For example, is that if we go into a valley, you have your uplands, which tend to be relatively steeper slopes, not necessarily higher velocities. And these are places, though, where you're more likely to have erosion. And in the intermediate areas, like the upland valleys, that there's going to be sediment transfer, a temporary storage of the sediments. And then when you get down here, you'll have your deposition, long-term storage of those materials, really down in the bottom of the valleys. This here is another graph that's really showing how velocity of the water and the diameter of the particles determine whether you have erosion of those materials, just simple transportation, or deposition. And so those larger particles, for example, are more likely to be deposited, and as you go higher and higher velocity, more likely to erode those materials too. The authors state that floodplains form during periods when deposition predominates and channel incision occurs where erosion predominates. What we'd seen before, for example, were examples of both deposition but also that channel incision, the removal of materials where water velocities are highest and the gradient is often steepest. In the Amazon, for example, more sediment is transported laterally to the floodplain than to the ocean. So you have materials that get picked up by the Amazon River and they tend to be deposited in the adjacent floodplains, building up those soils a lot more so than just being taken out and put out to sea. Sediment transport, though, is really important in depositional areas out in the ocean. So this is the delta of the Mississippi River. And these deltas are really important because these are still depositional zones at the ends of the rivers, and these are important habitats and have important ecosystem properties here. This is another delta for the Yukon River in Alaska, and you can see a very braided situation, but a lot of deposition in this area. Sediments are very important in ecosystems, not only because they're taking out materials, but where they're deposited, they're important ecosystems, and the sediments are important for maintaining those ecosystems. In general, the authors state that erosion of terrestrial material to the ocean is about 1 to 10 millimeters per century. So a given area is going to have 1 to 10 millimeters per century of material removed. In this table, table 3.1, shows the different erosion rates that you have for different climatic zones. And again, this you can see essentially it's millimeters per century, and there are some places that have relatively high erosion rates, these steep valleys, for example, and other places that are relatively low, where you have gentle slopes, or in arid systems, for example, where you just don't have a lot of water that's going to generate the high velocities to generate erosion. So when we're thinking about erosion, it's important to think about flow, but also weathering, so the formation of soils as well as the processes that take those soils away. We really need to think about the trade-off between storage and loss and places where soils are lost versus temporarily stored or deposited. Humans have had a big effect on erosion, And it's estimated that somewhere on the order of 2.3 billion metric tons per year of soil are eroded due to human activities. But we've also had effects where we've reduced the sediment flux to oceans and lakes by somewhere on the order of 1.4 billion metric tons per year. So not quite the same amount of the increase in erosion, but we've also reduced sediment flux through other processes. Now I'll take a few moments to talk about dams, sediments, and water. And dams are the major factor that humans have done to reduce the amount of sediment inputs to lakes and oceans. So I'm going to talk about dams, sediments, and water using a specific example of a dam just upstream from where I live. Also our dams. This is a picture of Manhattan, Kansas in July of 1951, and this is the last major flood that we had in the region. So this is KS Hill, for example, and this is the road out of town, and you can see this is the area where there are houses. There's a lot of, this is downtown over here, and the river that passes through the city, or at least on the south side of it, had flooded most of the area. In response to that, they decided to build a reservoir or a dam for this river. And this is it here. This is the Tuttle Creek Dam. It's an earthen dam. It's one of the largest earthen dams that were built at the time. And so this is the top of it right here with the reservoir behind it, and Manhattan is downstream a little bit. And this dam for Tuttle Creek Lake, for example, here's Manhattan, drains a large area of both Kansas and Nebraska. And I bring this up because it's really important to see how temporary the storage of those materials are and how much material has been stored behind this dam. So it holds back water, but the outlet for the dam is right here, and most of the sediment that enters the reservoir doesn't come out. So this here is the distance from the dam itself, so upstream, and here's the elevation above sea level. And in 1962, not long after that dam was built, here we have the dam itself, or the base of the dam. And this was the elevation of the channel right there. In 1999, when they resurveyed it, we had material that had been deposited that had raised the level of the floor of the lake by somewhere on the order of 20 feet, all the way up to 40 feet right here. And you can see a large amount of sediment that normally would have flowed out of that area have been stored, at least temporarily, behind that dam. And this is something that's really general, for example, in dams all across the world, is the storage of those sediments. Now, one of the problems with all this storage is that this is the top of the dam. And when that dam was built, essentially the top of the dam was equal to the top of the channel bed in 1962. But since then, there's been enough deposition such that it's really reduced the amount of water that can be stored behind that dam. And again, that dam was set up to store water, but it's also stored sediments. And if you look at all the material that's above the dam right now, if all of this were to move down here, it essentially would fill up this whole area, such that there would be no room left to store any water. Now in 1993, we had a large set of rains that had occurred that had filled up the area behind the dam and had essentially flooded over the dam, and they had to open the spillway that's here and release large amounts of water. As a consequence, because that dam could not hold all the water, there was localized flooding in the area, but it hadn't necessarily breached downtown. This is areas outside the levee, for example, that were flooded, but downtown, because it was behind the levee, wasn't flooded. Because of all the storage of sediments that has occurred since then, if that same amount of rain were to fall, the dam wouldn't be able to hold it back, and essentially the water would run right over the top. So by setting up these dams, we've stored a lot of sediments, for example, but we've also reduced the capacity of these dams to hold back water. And their initial purpose of reducing the likelihood of floods basically no longer exists. And it only took about 50 years for that to happen.